Hi, today we'll be talking about assembly language programming. We're going to be using an example to actually demonstrate this, and it'll be 68,000 microprocessor. The problem we'll be facing here is under this description, which is write a 68,000 assembly code to calculate powers of base E using the first 7 terms of its power series. And obviously we need to identify 7 terms, as you will see here, that the summation here will go up to infinity, and we can't do that practically. So initially we will obviously have to read if the x variable here, the question is asking us here. So the x variable will be stored in location xval, and we have to return the result at the location e to x, and the power series is e to the power x, which is equal to the summation x to the power n divided by n factorial. That's what we'll be doing today. And n here goes from, the summation goes here from 0 to infinity. And as I said earlier, we have only the first 7 terms, which is 0 to 6. So we start with initiating the variables here. And before we do that, we obviously need an origin for address purposes. And we can choose randomly 5,000 here in this case. And xval will be our first variable that we initiate, and we use obviously direct constant with word as its length, and we can use this an example here, again randomly chosen 4. We could have used maybe 5 or 6. There's a limit to this. We won't be talking about this today, but the limit is to do with overflow and the fact that we're using 32-bit microprocessor. So the other variable that we discussed will be storing the data, the final answer, which is e to x. That's the question asking us to call it that, and we'll be using ds instead, and 1 for 1 word. Now we're left with other variables, so we can easily see that it'll be a good idea to use to initiate n here instead of using a register as our variable, and we initialize it 0 because we were doing like a for loop that goes from 0 to 6, hence it starts with 0, and that's our initializing. We initialized the for loop. Now we get into the equation and the program. I'm gonna leave a space here because obviously I know I'm gonna be adding something here later, but for now the sum loop we'll be talking about initialize. We start with the for loop, and the for loop has to actually loop. In assembly code you need to go back and repeat the for loop as many times as you want, or the question wants, which is in this case to 6. So we have to use this line of code. So we're gonna add immediate, and we're working with word, one to our n, because we're gonna be looping n times. Now that we're adding n, and we have to know when the loop will stop. So basically we have to use a compare in assembly, and we're using immediate word up to 7. So we want to compare 7 to n with n. So now that we have that, we can stop the loop if it's lower than 7. If n is lower than 7, it will loop again, and if n is greater than 7 or equal to 7, it will stop the loop. And to do this, we need that branch less than branch, and obviously the label sum loop. Now that we have all this, we can proceed with the actual program. So it's gonna come above this. So we want to store n value temporarily in a register, because that we start with the factorial. Actually, let's talk about the factorial here. Let's do the factorial. There's different ways to approach this, but for this specific example, we're going to break it down into these different parts. So we're going to have loops for the factorial and loop for our power here, x to the n, and we've already started our sum loop. So in this case, let's start with the n factorial. And to do the n factorial, we need, the n will be changing from the n value, and like we already know, let's say n is 3, for example. What will happen is it's 3 factorial will be 3 times 2 then times 1. So we see that n is changing, and to do this we will need a register to store the n value temporarily. So we do move n into register 3, and we need the actual final answer for that factorial, which will use d4, and we're gonna have that value that's stored in d3 stored in d4 as a final answer. The first thing that comes in mind, actually we can start with the factorial right away, but the first thing that comes in mind is that when in factorial, when you have 0 factorial, the answer should be a 1. So if we did the regular multiplication and subtraction, the 0 value will not apply to this factorial. Like if we did 3, we know it's 3 times 2 times 1, but 0 factorial is a 1, is not 0. So we need to do some sort of a condition here that branches outside that factorial problem we're doing. So it would be factorial, let's call it factorial 0 label. So that's going to come after the program that we're going to write. Factorial 0, we're going to branch to it if the n is 0. Basically, if n is 0, we're going to branch to fact 0. And fact 0 is basically making the final answer to a 1. So our final answer is 1 in the case of a 0 factorial. And this will obviously happen because we initiated n as 0. Hence, we will encounter that situation where n is 0. So our d4 will store 0, but that doesn't happen in factorial. We cannot have 0. So it has to branch to this label where we are actually forcing the d4 to be a 1 only in that case of 0. And how do we do this? We obviously need that similar thing we do in this loop for the summation. We will do it for the factorial. So basically, let's start our factorial loop. So now if we start with a 0, n is 0, we need to do some sort of comparison and branching. So the same thing we did with the sum loop. So compare I for immediate, and then if the value is 0, that's exactly what we're looking for. We're comparing d3 with 0. Now if d3 is 0, it will set the conditional codes accordingly, and we want it to branch if that's the case, if it's equal to 0. Now if you want to talk more about this, but branch equal to 0, it means that your 0 flag will be a 1. And in that case, you want to jump to factorial 0, label that we just created. Now that we have this special case in factorial taken care of, we can actually continue with what we are familiar with in factorial, which there's multiplications obviously going on, and decrementing that value. So the first thing we do is obviously subtract 1 from your register D3, which has the value of that n initially. So that's what we're doing. Subtracting immediate with word W, number 1, because we're decrementing by 1 each time, and storing in D3. Now, what would make sense here, obviously, you're going to be multiplying because we're doing a multiplication. So we'll use MULU for unsigned values, and you're multiplying D3 and D4 and storing in D4. So the D3 had the value, the previous value, which was decremented here, and D4 has the previous value, and D3 was decremented and multiplied. So let's just go through an example quickly here. If you had a 3 here for n, it will be stored in D3 as your bucket register, and that D3 is going to be decremented by 1. So basically you'll have a 2, and D4 here had that 3, so you'll end up multiplying 2 and 3 and then storing the result in D4, which is 6. And that's exactly what a factorial does. So we are really done with that factorial equation, but now we have to know how many times we're looping within that factorial label. So similar to anything else we do with the loops, we have to branch somewhere. So we want to branch back to that factorial. So in order to do this, we do that same compare immediate, and you're comparing it with a 1 because we want to know if D3 is greater than 1 or not. If D3 is greater than 1, then we want to keep doing the factorial. If not, we have to stop doing the factorial, obviously, because the last number will be a 1 in a factorial. So we do 1 and D3, and then we will branch if it's not equal to 1. If it is equal to 1, if it's not equal to 1, we will branch to factorial. And that's exactly what we're looking for. So basically we are branching to factorial if 1 is not equal to D3. Again, it's to do with the conditional codes that were updated based on the compare instruction. So now that we have this, actually completes our factorial function. However, this line will force D4 to be a 1 again. So we need to do something here that will stop us from branching. That we need to branch away from this. So in order to do this, we will branch always to the line after the fact 0 label. So branch always. Let's call the new label calculate the power, because that's what we're going to be doing. We're going to be calculating the power x to the n, because we're done with the factorial. Now we're going to calculate x to the n power. So we just call it calc power. So calculate power. Now that we have this, we're going to actually create the label for it. And then we start programming our power calculations. Now, We need also the same thing we've been doing earlier. We need to store the final answer of this portion of the equation to a register. We can use register 6, for example, and we initialize with number 1 as an example. So now we initialized, we stored 1 into 6 for using as the answer x to the power n. And the reason is because that's the lowest number you can get. You won't get a 0 when you're doing x to the n. You won't be doing multiplication. And obviously we need to store n in another register for the multiplying how many times. So n times. We're doing n multiplications. So x to the power n means you're multiplying x n times, and you need to identify that in a register. For example, move n and n in a register 5. So now register 5 contains the n number of times we're going to be multiplying our x. So d5 is going to be used to, it's like a counter. It's going to be the loop counter of how many times we're going to be multiplying our x. Obviously we need to end. In this case now, we need to end the loop when finding x equal to 0. Again, the case where n is 0 does always apply. Like initially we started, our n is 0. So in this case, we will have a problem with x to the power n. Just like how we did with the factorial, you need to branch away from this. Calculate power when you have the case where n is 0. And to do this, we can easily use the instruction set branch when equal to 0. Branch when equal, basically to 0. And this happens, it's going to read the d5. And if d5 is 0, it's going to branch elsewhere. And where we're branching to another label here that I will call power e for now, which finishes actually the division here and finishes the loop. So we will need this label eventually. We called it power L. We will need this. We will need to use this eventually. Power E, sorry. Just notice I used power L. Okay, power E. Now we're branching from this because we do not want to do that calculate power if n is 0. That's the whole idea. So now we go into the actual multiplication. And we know we're going to be looping here because we're multiplying several times. So we need another loop label called, we can call it power L this time. And then what you're doing here is multiplying your x's. This is where we will use our x val that we initiated here 4, because you're doing x being 4 and you're multiplying that n times. So the power L here will have multiply unsigned again word, and x val is the term you're going to be using for your 4. And you're multiplying with what's stored in your d6 register, which initiated here with a 1. And this makes sense because you're multiplying x by a 1 in the case of n being a 1. So in the case of n being a 0, it's not going to go through this loop, which is not finished yet. It's not going to go through this loop. However, if n is 1, it will do it, and it will work because you're multiplying 1 by your x value, which is a 4. And you will get a 4. Now and you will see that as you increment, you will realize that as the values increase, you realize that it works in all cases. So now we did the multiplication. Now we need to know when to stop that loop. Initially I said that d5 was used to as a loop counter. So now we need to decrement the d5 by 1 as many times as we need for n times. So basically here we do subtraction using sub I for immediate again, and w, and you decrement by 1 the value stored in d5, which is your n. So we're decrementing d5 as our loop counter, and then we need to branch, obviously, if it's greater than. So if d5 is greater than 1, we want to branch back to this label so we can keep multiplying, because the loop is not done yet. And when it's not greater than 1, we will go to the next line, which actually has the continuation of your code, which is your power e here. And what it is, now that we have done these separately, the factorial and the x to the power n, and we also considered our special cases in the factorial and the special case in the x to the n. The special case x to the n is when x is 0, n is 0, and you want to just jump to the remaining of the equation, which really is you're doing that final summation. And actually you're going to do a division first between these two sets of, between these two partial equations, and then you're going to do finalize the summation. So what we're doing here is power e. We're going to do the division, obviously, because now we have x to the n and n to the factorial. Now we divide these. We divide the stored final values of each of these equations, the factorial and the power, which is x to the n. So we know it's d4 and d6. So div for division, unsigned, word, and then you're dividing d4 and d6, d6 being your x to the n, and d4 being your factorial result. Now that you have done this division, we need to increment our n value, because again this is the loop for summation, which we did initially. Now that we have basically the factorial part, and we have the x to the n, there's one line here that had to be done, because now that we actually divided these x to the n and n factorial, we have to actually do the physical addition. And this we can easily do by just doing an add d6 and a new register to store it in, which is d7. But now d7 was never introduced. We need to, well, the register usually starts with a 0. However, if we're starting a new program from a previous one, the register 7 could have values that are non-zero. So this is where the gap that I said earlier, I'm sure we're going to have to add something to it. We have to clear register 7 so it can be used here with no errors. So now we're adding this d7, which is the previous term, to the new term d6. that we just did for the division. So initially D7 was a 0, and then we're adding that 0 to our newer summation here, what's in there, and storing it in D7. So now the new D7 will have the D6, and then the new D6 will be added to your previous D7 terms. In this case, we will finish this loop, and then you keep doing that summation until your n is finished, which is 6 in this case. And this actually finishes the program. However, the question is asking us to store in E to X, not just D7. So the address location E to X, which we initiated here. And to do this is as simple as moving your D7 value into your E2X location in the memory. So move .w register 7's contents into address location in memory, that is E2X. Different ways can be done. Actually, this actually finishes this one method of doing this program, this equation. One can easily say it can be done a little bit more efficient by joining these maybe two together in one loop instead of having three different loops that we did here. The fact is, I'm just trying to separate these terms so it can be easier to understand. However, it can be done more efficiently than this by joining this. That's one thing. Others I've seen, like I've seen an example of a student that actually would do some pre-calculations of some variables. However, the best way to do this is to allow the assembler to do all the calculations for you. I hope this helps to whoever needs it. Thanks for listening. Actually, before I dismiss this tutorial, I think it's a good idea to run this program and see if it actually runs correctly, and to see if the answer is right. Now, obviously, mathematically, if we're testing it with x is 4, like I said earlier, we couldn't have used more than 4. And for overflow, or the fact that it's a 32-bit microprocessor, the thing is, when you work with multiplication here, and the x here, this 4, so you're actually doing x times x times x, like in this line here, what will happen is, if you multiply 32-bit and a 32-bit, what will actually happen is you get a 64-bit answer, and this doesn't work. So that's one of the main reasons why x should be like 4. But anyways, like I said, this was not part of this tutorial, however it's worth mentioning. So obviously, and the main reason we have n is 6 here, maximum 7 terms, which is up to 6, 0 to 6. Obviously, we're not going to the infinity, and due to that fact, we're not going to get the exact accurate answer, because you're not adding up to infinity times. You're adding up to 6 times. And that is a big difference between 6 and infinity. But the good news is we can get a good approximation due to the fact that as we approach infinity, this division here becomes very small because of this divide by n factorial, and you talk about infinity here, so that will be a very small number as you approach infinity, hence you're summing almost 0 as you approach infinity. So we should get a good approximation up to 6. It won't be perfect, but it'll be, well, I don't want to call it very close, but close enough for the purpose. And like I said, this is a very good example for people who are learning assembly initially. And so I did this small just pure math here to see if it actually, or to see what we will get using our program. What we should get with x is 4 here, as you see, I put 4, and n here up to 6, 0 to 6, and your final answer D7 should be 2e. So the final answer should be 2e, and 2e really is 2e in hex. Obviously the answer will be in hex. 2e will give you a 46. So it's not gonna be exactly what it would be. So let's see what it will actually be, e to the power 4, if assuming obviously n is infinity. So go scientific here, 4 inverse e to the power, so it should be 54. So our answer is 46 as opposed to 54. Now, like I said, 46 is, we can consider it being close enough, especially we're going up to 6. Now let's see if actually our code will give us 2e. So we run this and no errors, no warnings, that's good. We run this and then that's what pops out, and now we get we start running. You can either trace it line by line or do auto trace or do the whole run. So let's do auto trace just so we can have fun looking at this moving. So we see that it's looping according to the code, and obviously the registers are being updated with their values, and this is our D7 here. This is this D7. So the final, when it stops looping, the final answer here should be like I said, 2e, which is really 46, and here it's in hex. The registers save the values, so we should see 2e at the end of this operation in D7. And one good thing to point out is the reason why it was a good, we could have just stored it in e2x directly, as the question's asking, but the thing is, this is pointing to an address location, and it's not that convenient because we wanted to see the answers right away. If I didn't store in D7 like I did here before I transferred it from D7 or copied from D7 to the address location the E2X is pointing at, we couldn't have seen it here. But still, the answer would have been right, and we would have went into view memory instead. And it's an extra step. However, the answer is right here. We can see it stopped looping and it stopped changing here. And what it is, the answer is 2e, and it's right. It's correct, and as we said, it's 2e here. And I hope this helped whoever needs it, and thanks for watching.